Okay, so we're going to look at the torque and rotational motion practice questions. So for the first one, we're saying the diagram below shows a top view of a child of mass m on a circular platform of mass 2m that is rotating counterclockwise. Assume that the platform rotates without friction. So that's a good idea, this without friction. This means we don't have any outside forces and therefore outside torques acting on our system. The system is just the child and the platform. So the first thing we want to know, the first question about this is, which of the following describes an action by the child that will increase the angular speed of the platform child system and give the correct reason why? So if we kind of look at this setup, we can say, well, the system is made up of the platform and the child, and we already established that there's no outside torques acting on our system. And again, we said an outside torque will change the angular momentum of the system. But in this case, we don't have any change in angular momentum. So that tells us the initial angular momentum has to equal the final angular momentum. And then like we did with regular momentum, we can kind of split this into the pieces. We can say, what has angular momentum in our system? What's the total angular momentum? What is that made up of? In this case, we can say, well, the initial angular momentum is made up of the initial angular momentum of the child and the initial angular momentum of the platform. And we can say that the final angular momentum is made up of the angular momentum of the child final and the final angular momentum of the platform. And then what we can do is kind of split this into our pieces. We said that angular momentum is equal to I, the rotational inertia, times omega, the angular speed. So we can kind of write this out and say, well, we can replace angular momentum of the child initial with I child initial times omega I plus everything, kind of go through, do that for all of our objects. Then one thing we can say is, well, everything's rotating together. Like the child is on the platform, they're not moving like against each other. So the angular velocity is going to be the same for the child and the platform. So we can kind of call this one common omega I. And then we can say the same thing at the end. Afterwards, after something happens, again, we'll have this common omega final. So what we see here is what we want to do is we want to increase the angular speed. Yeah, we want to increase the angular speed. So we want this omega f to be greater than omega I. And it looks like if we have to have this equality, in order for that to happen, it looks like our moments of inertia have to be big in the beginning. I was going to write that big and then I ran out of room. So it has to be larger in the beginning than it is at the end to make this stay constant. We want to increase our angular velocity. We have to decrease our moments of inertia to make sure that this is conserved. So this is bigger in the beginning so that the omega can be larger at the end. So all we have to do is change our moment of inertia. We have to decrease it. It goes from big to little. And we have this idea that the moment of inertia is related to the mass times the distance from the pivot point squared. So we're not going to change the mass of our child or the platform, but it looks like if we can change r, then we'll be good to go. So it looks like what we can do is we want to have I decrease. So it looks like we have to decrease r. Sorry, I said that backwards. So yeah, we want to make I go from big to small, so it looks like we have to decrease r. So let's see which one of these follows that idea. Child moves towards the center of the platform, increasing the total angular momentum of the system. No. Child moves towards the center of the platform, decreasing the rotational inertia of the system. Yes, so that's going to be R1. We're saying, hey, we're going to decrease the rotational inertia, which will change our rotational velocity. Then, which of the following describes an action by the child that will result in an increase in the total angular momentum? So we already said before that this is a closed system. The platform and the child is a closed system. And within a system, if there's no outside torques, then the angular momentum is going to be conserved. So if the child moves towards the center, no, that won't change the angular momentum. Moving away, that won't change it. Child moves along a circle, that won't change it, because none of these have an outside torque acting on our system. Everything in here, yeah, we have torques acting on our system, but they're torques that are already inside of our system. So we have internal forces, but no outside forces, and therefore internal torques and no external torques. So none of these will actually be able to change the angular momentum. All right, this one's tricky. A meter stick is held as shown below and then released from rest. The tabletop has negligible friction. Which of the following, or which figure best indicates the path of the center of mass of the meter stick as it falls. So this one's weird. What we're looking at here is kind of a torque problem, but we're looking at this pivot point here and then kind of going from that situation. So our pivot point is along the table, but we kind of have this moving pivot point. So when we are dealing with torque problems, we say the torque is equal to R times the force. In this case, yes, we have the normal force acting on our rod, but that's happening at the pivots. That's not really causing a torque here. So really the torque in the system is coming from just this gravitational force. And while this is happening, so we have this torque caused by the gravitational force, which means that yes, our rod is going to rotate down. So while this rotates down, the rod is going to move out that way. It's frictionless. So pretty much what we have is the gravitational force acting straight down through the the system's center of mass, with no forces that are going to change this thing's ability to kind of pivot. So it's just going to spin down just as a center of mass with no other really forces acting on it. These will just kind of slide out of the way. So really all that we have is it's pretty much a object with mass with one force acting on it. Yes, we have these forces, but they're kind of sliding and getting out of the way. So really all that we have is just an object with gravity acting on it. So it's actually just going to be C. There's going to be no other forces that will make it move in this direction, because normal force is just kind of acting against it, but that's kind of sliding out of the way and not torquing it. So we just have this straight up one object going straight down. So we just have C. All right, with this one, the figure below shows a rod that is fixed to a horizontal surface at pivot P. The rod is initially rotating without friction in the counterclockwise direction. So it's initially rotating counterclockwise. At time t, 3 forces of equal magnitude are applied to the rod as shown. Which of the following is true about the angular speed and direction of rotation of the rod immediately after time t? So it's initially going counterclockwise, and that's kind of a big deal in this question. Then when we look at it, yeah, we're going to have some forces. This force will apply no torque because it's acting at the pivot point. And then we have kind of this comparison. We say, okay, well, we have these two forces acting in opposite directions, but we say torque is made up of R and F. So we have the same F in both these cases, but because R on this right side is bigger, our net torque is going to be in the downwards direction, which will cause us to spin clockwise. So our net torque is in the clockwise direction. And then kind of the idea that we have here is, yes, our net torque is in the clockwise direction, but we're asked immediately, so right when this is happening. So this is not going to immediately come to rest and then start spinning in the opposite direction. It'll happen over time, but it has like this inertia. It has inertia that's causing it to be moving counterclockwise. It's already doing that. In order for us to go from counterclockwise to clockwise, we have to stop and then start spinning the other way. So yes, this will slow us down, but it's not going to immediately change our direction. So it'll still be going counterclockwise. So it won't be clockwise, but we see it's going to slow down. Our net torque is opposite, so it'll slow down. It's kind of like if we were thinking of an angular or a linear equivalent. If you had a car that's moving in this direction, and then you turn on the brakes, that's going to be a force to the left, but your car is still going to be moving in this way. It'll just be slowing down. If we like kind of draw a motion map, it'll be slowing down. So it won't immediately turn around. That would be annoying if like every time you hit the brakes on your car immediately turned around. It has to stop, come to rest, and then eventually it could start moving the other way if we keep on applying that force. So that'll be A. All right, with this one is difficult. A thin rod of length d on a frictionless surface is pivoted about one end as shown below and can rotate freely. The rod is at rest when it is struck by a sphere with linear momentum of magnitude pi perpendicular to the rod. The surface rebounds along its original line of motion with momentum of magnitude pf. What is the magnitude of the angular momentum of the rod immediately after the collision? So this is a difficult situation where we're looking at angular momentum, and it's weird to think about, but this ball, it technically has angular momentum, especially if we kind of stop it right at the moment where it's in line with D, or in that line D that we've kind of drawn, in line with the rod. So we can say that this ball at this moment has angular momentum around this point. It's technically pivoting that point, which is really weird to think about. But technically, like if we kind of pause it right here, who's to say? Maybe it would keep on going that way. It won't. But at that time, technically it does have angular momentum around that point. If we were going to make this ball do a circular path, there would be a point where it would be just in line like that. So maybe, yeah, what we say is, yeah, technically at that point it does have angular momentum around that point. So what we want to look at here is this ball and rod system and look at the angular momentum. So what we can say is the ball initially, it's technically kind of rotating in the counterclockwise direction along this from this pivot point. So technically it's moving like this, which is technically a counterclockwise motion. So it technically has this initial positive momentum, this positive angular momentum. And the rod is not moving initially, so it has no angular momentum. So the total angular momentum in our system is just L initial of the ball. And then we can say afterwards, same kind of thing. So for this time, it's going downwards. So technically it has this clockwise angular momentum. So technically it has this negative LF for the ball. And the rod, it started spinning, so it's spinning in the counterclockwise direction, so it technically has this positive angular momentum. So we can say, okay, well our final angular momentum is LIB, just like before, L initial for the ball, is made up of L final for the rod minus L final for the ball. So if we kind of rewrite this, we want to figure out what's the angular momentum for the rod. So we can solve this in terms of the angular momentum for the rod, and set that equal to L initial of the ball plus L final of the ball, just by doing some little bit of math. Now this is where the tricky part comes in. So what we can say is, well, we know that angular momentum is rotational inertia times the angular velocity. So we can say the initial angular momentum is the rotational inertia for the ball times its initial angular velocity. And then same thing for the final situation. And what we can say is, for just a point mass with like no shape to it, the rotational inertia for a point mass is just mr squared. And in this case, the r, the radius, the distance this is from the pivot point, is just going to be d, the length of the rod. So we can say the ball has rotational inertia of md squared. Now we just need to figure out the omega. We need to figure out the angular velocity. So we say, okay, we kind of have this idea where the circumference of a circle is 2 pi r, so this is us just plugging in theta. So we can use that same trend and then kind of rewrite and say, well, our angular velocity for the ball is just going to be the velocity of the ball divided by the distance from the pivot point, this r. In this case, we said the distance from the pivot point is d. So now we have an expression for that, and we can say, well, the initial angular velocity of the ball is just going to be v initial divided by d, and for the final one, it's going to be v final divided by d. And now we can solve this. We can say, well, L initial, we said, well, our rotational inertia is md squared, and our velocity was vi over d. So we can rewrite this as mdvi. And then we know, well, momentum is just mass times velocity, so we can really rewrite this as the initial momentum, pi, by multiplying these two, times d. So m times vi is just equal to p initial. Same thing for the final. We can say, okay, we got this whole situation, and then m times v final is just p final, the momentum final, times this d right here. And then what we can say is, well, we wrote an expression for L final for the rod as L initial ball plus L final ball. So that just equals P final plus P initial, or P initial plus P final, times D, because they had that D in common. So we kind of factored that out. So yeah, that is a very tricky question. And yeah, that's kind of what we got.